Good morning, and it looks like the last talk of the day, as we have a break in the afternoon, is Adela Zhang, who's going to tell us about open-closed bordisms and TFTs.
Okay, thanks Mark for the introduction, and thanks for inviting me. And I'm going to talk about something that's not quite related to telescope conjecture, but it has THH in it, so hopefully we draw some nice pictures and everything will be clear. So yeah, so I would say that this is joint work with Charles Barkin and Jan Steigbrunner. And let's start by fixing some limitations. So let's consider consider 1 to be a metric monoidal infinity 1 category, maybe just infinity category. And I also wanted to have all geometric realizations. And suppose that A is an E1 algebra in other words, you can also think about an E1 algebra as a symmetric modular functor, also called A, from the infinite category of oriented one disk to D that sends the object D1 here to A. And here we're using the fact that this category of oriented one disk, this is the symmetric modular envelope of the E1 operand. So in other words, E1 algebras are characterized by symmetric modular functors out of this category. Okay, so, and okay, maybe let me just define more precisely what this one OR is. So this is the sort of the infinity category, infinity 1 category with objects, disjoint unions of disks, and morphisms are embeddings of disks. And this sits inside a slightly larger category, sort of the category of compact manifolds, one manifold with boundary. And so the objects will be compact one manifolds with boundary, and morphisms will be embeddings of those. Okay, so now let's try to define THH. So of course, like THH is defined for any E1 algebra A through the cyclic bar construction. So recall that THH of A is the colimit over n in del of the cyclic bar construction of the E1 algebra A. And pictorially, the cyclic bar construction can be captured as follows. So you have a circle. You have a circle. You have a bunch of points labeled by elements in A. So in each level, it will be, each level of the bar construction is A tensor to the n plus 1. Sorry, there's a plus 1 here. So it's going to be A1, A2, all the way around to n plus 1. So there are a bunch of points. And the face map in the cyclic bar construction is given by multiplication. So you collapse adjacent points using the E1 structure in A. The multiplication, or face map, is given by, so you have all the other points intact, but maybe you want to multiply A to an plus 1, it's like AI and AI plus 1, and do so by just colliding them. So you replace this with a single point. Wow. With a single point, and now I label it by AI plus 1, AI tensor AI plus 1. So because we're using the clockwise rotation, so that's why AI appears first and then AI plus 1. Maybe I should use the green color. AI tensor. Okay, so hopefully this is something that everyone knows. It's sort of the classical definition of partial homology. But on the other hand, we can do a more geometric construction. So these little points here, they're the same as little intervals. So I can just, instead of considering an n plus 1 point, I can instead consider now I still have the circle. So now I have n plus 1 intervals, all again labeled by elements A1, A2. All the way to n plus 1. But now colliding points are represented really just by embeddings of two intervals into another. and again, when labels AI and AI plus 1, AI and AI plus 1 get set into the label AI tensor AI plus 1. So this sort of motivates the equivalent definition of THH of A as the factorization homology. So this is the same as the factorization homology of A over S1, and this is explicitly is the co-limit of the following functor. So I can take my disk one oriented category. So maybe for the rest of the talk, I will usually just write this as disk. So I can take all ways of mapping my disk into S1. So you see these little intervals, they sit inside S1. So I take the slice category over S1, and then I can forget disk, and then I map using the equivalent definition of even algebra into B, and I take the co-limit over, I'm taking the co-limit over this over S1. So this is the factorization homology of A over S1, and these two agree. So the fact that these two definitions agree is really using the fact that disk over S1, this is equivalent to the one category, which is the paracyclic category. And the paracyclic category is self-dual. And the nerve of the op maps, there's a cofinal map from the nerve of the op to the nerve of the paracyclic category op, and it's given by ascending n to the poset C cross n. So if you like unwind all these functors too, you will see that okay, they're really computing the same co-limit along this cofinal functor. Okay, yeah, so this is the version of THH that we want to use. So usually we'll just write factorization homology for all the THH that we are trying to compute. Okay, and more generally, so I define factorization homology over the one manifold S1. So more generally, for any n in manifold 1, boundary, I can define factorization homology of m of A over m as the same co-limits, but I replace S1 with m. So it'll be co-limits over all the ways of mapping the disks into embedding my disk into the one manifold M, and I take A tensor D, as in D. Every D here is n copies of disk, so I'm taking A tensor n. Okay. So to state our sort of an application of main theorem, maybe I should make one more definition. So again, we fix this V globally, and suppose that A in V. Okay, so the definition is the following. So A in V is an E1 Calabi-Yau object if A is an E1 algebra together with a certain trace that goes from the factorization homology of A to the modular unit, let's call it tau, that is invariance under the SO2 action on the factorization homology, which is the circle action on the manifold, invariance. And furthermore, we can precompose with the map from A tensor A, which is the factorization over the disjoint union of two little disks. And these two disks embed into S1. So this map to the factorization homology of A, and then I compose with the trace. So this map, this pairing has to be non-degenerate. And furthermore, it exhibits a self-duality of A. Okay, so classically, these E1 Calabi-Yau objects are known as symmetric Frobenius algebras. So classically, when V is the one category of vector spaces over a field K, So E1 Calabi-Yau is the same as symmetric Frobenius algebras. And in V, and this is using observation that the homology of A, it's really just A, quoting out by the commutators, it's the center of A. So yeah, and that's sort of the definition of a symmetric Frobenius algebra. Okay, so now I think I have introduced enough notations to tell you a corollary of we did this theorem, three of us, so Shao, Yan, and myself. Suppose that A is an E1 Calabi-Yau object in V. Then there's an action of the moduli space on the factorization homology of A, and this moduli space is B diff, if there's some notation, sigma G2n partial on factorization homology of A. And here, the notations means that, so G means that it's a genus G surface, oriented compact, genus G with two circle boundaries, and the n is n punctures. So pictorially, I have an incoming boundary, an outgoing boundary. I have some genus, and I have some punctures. And this little partial here means that the diffeomorphism should fix the boundaries, fix the S1, but it can freely permute my punctures. Okay. Yeah. And more generally, we can ask, okay, so these are sort of maps from the factorization homology of A to itself. So what about, we can consider multi-area operations. So what about maps in V from, say, I copies of factorization homology of A, and then factorization homology of A with J copies. So now we have to put this little slightly strange condition that I has to be at least 1. So there's a sort of a map from B diff, fixing boundary of sigma G. Now I have I incoming circles, J outgoing circles. So I have I plus J circle boundaries and a bunch of punctures. So again, so this will be moduli space with I circle, I incoming and J outgoing, and I circle is 1, and then some genus, some punctures. Yeah. So, and in particular, when J equals to, so if we just fix J equal to 1, this tells you that the factorization, the THH of A it's really an algebra over the surface of red. And morally, what this is saying is that, so in fact, these moduli spaces with various genus and punctures, they capture all the sort of the natural formal operations of the THH of a E1 Calabi-Yau object, and we'll make this. I will try to make this point more precise later on. And the remark is that so this theorem, or this characterization of sort of the universal operation, was proved by Costello when V is the sort of derived category over Q, chain complex over Q, and by Natalie Wong when V is over the integers. And so our theorem is sort of a space level refinement, so we're really considering mapping spaces. Okay, so maybe now it's time to give some really concrete examples. So what are some Calabi-Yau objects, E1 Calabi-Yau objects that appear in nature? So one sort of canonical example, so this is not technically an E1 Calabi-Yau object. So let's take M to be a closed-oriented d-dimensional manifold. Yes, and R just any ring spectrum. Then the cochains of M, values in R. This is really a twisted Ivan-Kavi object, in the sense that, so we do have non-degenerate pairing from A tensor A to itself. This is the Poincare duality pairing, but it does not go to the unit. It goes to unit shifted by D. So i.e. the pairing really is A tensor A goes to the factorization homology over S1, and then to A shifted to R shifted by, or to unit shifted by D. So how do we sheet and make it Ivan-Kavi? Well, so suppose that M is even dimensional. So if D is an even number and R is even periodic, and we know that there are plenty of them here, and then, then the cochains on M, the cochains R, is indeed just a Ivan-Kavi object. So then our theorem applies. And if we look even at a more special situation, so where we actually can identify the THH of this Kavi object, so if M is furthermore is simply connected, and R is K adjoining a pair of generator T, T is in degree 2, and K is a field, then we know that the THH of the cochains M, the values in R, is really the cochains on the free loop space of M. Yeah, so now we can really apply our theorem very kind of concretely and say, okay, so there are all of these moduli space acting on the cochains of the free loop space with coefficients in R.
Adela, can you maybe swap those two boards because we're blocking them?
Okay. So as I said, this is really falls out as a corollary of the theorem that we actually proved, which is about certain TFTs. But before that, maybe let me say a bit more context and set up a bit more notations.
Can I just check that your assumptions on B and the symmetrical nodal structure? You don't assume colimits and you don't assume that the symmetrical nodal.
Oh yeah, I do assume that geometric realization exists.
But no more colimits.
I mean, co-products?
But
Yes.
No interaction with the symmetrical nodal structure.
Yet,
Huh?
at some point, yes.
Okay.
As in like, yes, maybe in stating our theorem, we do want to compute, tensor product, symmetrical nodal structure should, the tensor product should commute with geometric realization in each variable. So it should preserve certain colimits, but nothing more. Okay, yeah, maybe let's make it state it. Tensor product commutes with geometric realization in each variable. Okay, okay, so let me give a little bit more context. So a lot of the things we do are really sort of done by Costello over the rationals, and so our story is really sort of a space that we're finding of that. So one thing that first, let me say a theorem that's by Xiaowu. So they kind of give a description or a classification of this Ivan-Kavi object. So again, fix V. So Ivan-Kavi objects in V are the same as in V. These are equivalents, which reduce there as the sort of an algebras over the cyclic E1 operad in V, and they in turn are classified by symmetric monoidal functors F from a certain bordism category O, called open bordism category 2B. And in particular, there's an object called D1 living inside O. And so going this way, you evaluate F at D1, and this will produce an E1 Calabi object. Yeah, so again, everything, so this is also proved by Costello over Q, but I think Yansha used like theory of modular operands to promote this to a space level story. Okay, so I have not really defined what this bordism category O is, and maybe let's do it now. So this already sits inside a bigger bordism categories that captures two-dimensional bordisms with corners. So board 2, or boundary, is the infinity 1 category with objects, compact oriented, one manifold with boundaries. So in practice, it will be disjoint unions of circles and closed intervals, and morphisms from M to N are two bordisms that are compact oriented surfaces, but might have corners. And maybe let me draw an example. So let's take W to be, there's my blue chalk. Okay, bad. It's here. Let me draw a morphism here. So I take M to be a circle, and I take N to be an interval. And what is the two bordism between the circle and the interval? Okay, I can just try to take the cylinder, but it's not really. We have to fill the surface a little bit. So we have to add a little bit of boundary here to make it really a surface. So this is already a cylinder, but here we really have a corner that's created by the intersection of this red boundary that's not part of the object data. So this is really called the free boundary. The intersection of the free boundary with this outgoing circle, or with this outgoing boundary, it creates some corners in the manifold. So even though our morphisms are like, it has corners, but it's not bad in the sense that all the corners come from the intersections of free boundaries with the object boundaries. So in other words, so the boundary of W should be the union of the incoming boundary, the free boundary, and the outgoing boundary. And furthermore, the corners can only be the intersection of the free boundary with the union of my incoming and outgoing boundary. So yeah, there's some singularity, but it's not too bad. And this really is disjoint union. So bordism here is just such an object, and the space of morphisms. So point in the space of morphism is a particular or two bordisms. So the space of morphisms from M to N is given by the disjoint union of the modular space B diff partial maybe Mn W. So for any diffeomorphism class of W that fixes the boundary M and N, we have a path component here. So again, the diffeomorphism only fixes the boundaries are the objects, but it's free to move the free boundary around. So if I have a circle boundary, I can just move it around freely. And maybe let's say one more word. So more classically, people might be sort of more concerned with version of board 2 where you only consider closed manifolds and no free boundaries. No free boundaries. And this sits inside this larger bordisms where we allow boundaries and a little bit of corners. Okay, so in order to maybe...
As you allow W to have closed components that do not touch the boundaries, M&M?
Yes, of course. So then you can always adjoin something like this here. Yeah, so this will be really M disjoining with empty, which is... Okay, so let me show you some more pictures to make sure that people understand. Work? Oh, too bad. Oh, okay.
We're gonna have a technical issue. There it goes.
Okay, yeah, so let me show you some concrete examples. So let me repeat, board 2 partial has objects, disjoint unions of circles and intervals. And the morphisms are compact oriented surfaces with some little bit of amount of corners. Okay, the color is not great, but I try to be consistent with the color scheme. So here the first bordism is from 2 copies of S1 to S1, so this actually lives inside the classical board 2. And the second one is from empty to S1. The third one, this does not live in the classical board 2 because there's a red circle. Can you see the red there? It's a little bit unclear in this coloring, but there's a red circle there. That's the free boundary. So I mean, objects are colored in blue and green, and boundaries that are not blue and green, they're really part of the morphism data. But we can have something that's more exotic. So the fourth one is the incoming boundary is circle and disk. Outgoing boundary is 2 copies of disk, and this really is a pretty wild-looking 2 manifold with corners. And finally, we can have these 3 copies of disk to S1 going by a cylinder. Yeah. And the point being that the boundary of our bordism really has 3 parts. So incoming, outgoing, and free boundary part that really belongs to the data of the morphism. And the composition here is by gluing outgoing and incoming boundary. So I have this, and because I'm only allowed to identify objects, I'm not allowed to do anything to the boundaries that are part of the morphism. So when I glue the blue and green interval there, so I got a little circle, free circle boundary. I bordism.
Can I ask, can you remember what's the relationship between the category O in the theorem over there?
I was about to say.
Oh, very good. Okay.
So now let me introduce a slightly smaller category. So OC inside. So this is in the title, so you should care about it. So OC inside board 2 partial. So this is white. Okay, this is a bad name, but which means it has the same object, but it only has part of the morphism, so it's not a full subcategory. And there's a boundary criterion that's saying that each path component of my bordism. So okay, maybe I did not say that, but you're always allowed to take disjoint unions. So your bordism can be disjoint unions of bordism of these manifolds. It can have many path components, but each path component in OC, the boundary of so each path component has to have at least one non-empty incoming boundary or one non-empty free boundary. So in other words, you have to have at least one of blue or red color in your bordism. If it's all green, then you're not in OC. And some examples. The first one is fine because there's blue incoming circle boundaries. The second one is not because circle boundary is the green one is outgoing and no free boundary, and it's from the empty GS1, so it's not in OC. The third one is fine because we have a red circle boundary, even though the incoming boundary is empty. And the last 2 ones, when you have D1s involved, you always have to fill in a red interval to complete your surface. So it's always part of OC. Okay, this is a slightly strange condition, but it is well justified. And now I'm finally ready to introduce O. So O is the full subcategory of OC on objects with disjoint unions of disks. So it also has this weird boundary condition, but again, once you have D1, you always have free boundaries. So some examples is like mapping from two D1s to one copy of D1. This is a flat pair of pens, but you can also have things that are more exotic. So this is the non-flat pair of pens, but also with the genus. And in particular, like this category that indexes, that really parameterizes E1 algebras, this sits inside O with the same objects, but it is not full. And if you have embeddings of disk, you can just so this is an example of how embedding 3 disks into 2 disks, and you can canonically turn it into an morphism in O. But things that are not just flat, they cannot possibly come from the disk category. Okay, so I will just leave it there. Okay, so hopefully everyone is comfortable with all of these. And let me do some erasing. Okay, so in particular, we see that, so in particular, because O already contains a category disk, I'm dropping all the decorations there, and in particular, D1 also maps to D1 living in here. So this gives D1 as an object in O, an E1 structure. And therefore, we're allowed to take factorization homologies of such things. And so now, given the theorem that Yang Xiao proved, so E1 Calabi objects, they're classified, or they classify symmetric modal functors out of this open category, open bordism category O. So one question people always like to ask in the sort of topological field theory is like, can we extend it to a slightly bigger bordism category? So maybe the question is, can we? So suppose that given an open field theory, so F going from symmetric modal functor from O to V, can we extend it canonically to, for instance, a functor from OC to V? Well, we know that O sits inside OC, so there's always a left count extension along the inclusion. However, on the left count extension, so a lower shake of F, this F priori is lax symmetric monoidal. Oh, okay, the picture disappeared. It's lax symmetric monoidal. But to be a field theory, you really want a symmetric monoidal functor out of OC, and that's sort of our main theorem. So the answer is yes, this is in fact symmetric monoidal. So yes. So the canonical extension of F from OC to V is symmetric monoidal. And here again, V should be preserved. Okay, so this is this V here, so it should have symmetric monoidal structure and the geometric modernization, and it should meet. And furthermore, if we want to evaluate, so going from O to OC, we added a bunch of circles. So we might want to know what's the value of our new field theory on the object circle. So if we evaluate the left hand extension on the circle, then it's given precisely by the factorization homology of the value at the disk. Yeah. Okay. And now it's sort of okay, I have not erased this board thankfully. So now this theorem just follows from the fact that now we really have a map from OC of I copies of circles to J copies of circles to here, and this is a path component living inside here. And maybe now it's time for maybe some remarks. Why?
So in your first figure, you say it's even more structure actually at this.
Where's more structure?
Not just apart from being div, but from some bigger space.
Where did I say that?
Like you said, for exist apart from OC.
So OC from here to here is a disjoint union of such things.
It's just union, okay.
Yeah. Okay, so maybe a remark is why OC, right? Again, OC after all is a very weird, there's a kind of, seems like an artificial category. Why not, for instance, going all the way to Bourse 2, partial? And there are two reasons. So computationally, you can just show that this is true for OC, this is just not, you cannot prove this for Bourse 2 partial. And in fact, OC is, in fact, computationally, it's the optimal category for this result to be true. But more conceptually, the reason is that, so S1 is a dualizable object in Bourse 2 partial. So if my field theory further extends to Bourse 2 partial, this means that the factors in knowledge, which is THH, should be a dualizable object in V. But THH is just hardly ever dualizable, or just it's not dualizable in general, so it just cannot possibly be true. Whereas in OC, because of this weird condition, such that this is not allowed, right? So circle is not dualizable. So somehow you drop this condition, and now you're allowed. You actually get a canonical extension. But to further go to Bourse 2 partial, it's really a property of your field theory on OC. Okay, so maybe let me say another remark. I was given more context. So maybe people might ask, why do you care about this? All right, so again, all of these are, they were proved by Costello over Q. Costello proved everything over Q. And so Costello was more motivated by things that concern Fukaya category, and I don't really understand this, is indeed a space level refinement of this. But another reason you might care is that so in Jacob's classification of TFTs, he sort of sketched a proof of a sort of a non-compact version of the cobordism hypotheses in dimension 2. So these are sort of fully extended TFTs out of infinity 2 categories that concerns bordisms again with boundaries and are oriented. So somehow there the story is slightly neater, but it's a sketch, and the starting point of this, or not sketch a proof. It's more like he sketched a strategy in one paragraph, and the starting point is our main theorem, and plus the theorem of Xiaowu and Yang that classifies Iwan Claudia objects. So somehow knowing how to classify open field theories and how to canonically extend to open closed theories gives you a sort of a non-compact version of the cobordism hypothesis. Okay, I don't want to develop too much on that, but if you're interested, maybe I can maybe just open the paper and turn to section 4, and you'll see the sketch. Okay. So now maybe let's talk about how to prove this. So our main theorem, so it concerns the fact of proving certain left symmetrical modal left conic extension to be actually a symmetrical modal functor. And the main theorem sort of it follows pretty formally from two categorical results. So O inside OC is full, but missing the circle objects. So this is a dense subcategory. And i.e., if I take the diagram that captures all ways So okay, first let me fix an object M in OC, and then consider a diagram that captures all ways of mapping from an object to O to M. So this is the value product of O to the size category of OC over M over OC. And there's a map going from OC to over M, size over M, and back to OC. So this diagram has colimit equal to N. So in other words, you take all ways, so being dense means that take all ways of mapping from your subspace O to your object that might not be O, but it sort of converges. And so that's what it means to be dense subcategory. And equivalently, this is characterized by saying that if you take the restrict unit embedding, OC first go to presheaves on OC, and then restrict it to presheaves on O, this is fully faithful. And this is the characterization that we'll end up using. So this is one categorical fact about how OC can really be obtained formally from O. The second fact is that, okay, so we know that any object in OC is the colimit of this canonical diagram, but in fact it's the colimit of a much smaller diagram. So we can take disk slice over M. Here's a map to our canonical diagram. And this is actually cofinal. So the colimit is really computed by the colimit indexed by this factorization homology diagram. Yeah, so, and morally what this means is that, so O is a pretty natural category, and OC can really be obtained by O by formally just adding colimits of this shape. And that's how you obtain OC. So maybe by this point you will see that in fact OC is not that arbitrary category. It really there's certain canonical colimits, you are joining it to O, and this is the category obtained. Okay. Oh, right, I forgot, sorry. Okay, so how do we prove these categorical results? So again, there is some amount of abstract instance you can use, but eventually it will reduce, we're reduced to trying to compute certain colimits. So, so these can be reduced formally to colimit computations. And so again, it's not a one-to-one correspondence, as the two colimits that I'm about to state together implies these two. So A. So first we know that in dimension 1, embedding calculus converges. This means that so for any M that's a compact one manifold with boundary, I can take factorization homology of M over D1 in one manifold. So you take all the ways of embedding your interval into your one manifold, so it should converge. But it's also true, and there's a nice proof that you can find in a paper by Sonner Coopers and Manu Kranek. But M and D1, these are objects in OC, and we can pretty easily deduce that, in fact, this is also true in OC. Okay, so there's one colimit that we more or less just obtain for free, and the second one is more complicated. This is in trying to do a colimit computation in presheaves in O. We want to show that. So let's take the factorization homology over S1 of the Uneta embedding of D1, the restrict Uneta embedding of D1, and again, this is the colimit over disk over S1 of Uneta of D, a bunch of disks. And so to be an object here means that you have a map. You're provided with data of map to S1. So therefore you can map to rho of S1. And these maps are just given by data that's coming from the slice category. And the claim is that this is in fact an equivalence. And so in the rest of the talk, let me try to sketch a proof, which is more or less a proof by pictures of this Copenhagen computation. Okay, so again, like, yeah. Sometimes it's a little bit confusing. So Unita, the sort of the pre-sheaf, in the pre-sheaf category, you formally join all colimits, but the Unita embedding does not preserve colimits in any meaningful way. So even though we know that the sort of the factorization homology of S1 D1 is the circle, it doesn't just tell us that this is true in the pre-sheaf category. Okay, so now we have to first do a little bit of unwinding to make this statement concrete. So unwinding, what it means to be the restricted Unita embedding. So unwinding the definition of Unita restricted, we want to show that for any object M in O, right, so we're trying to prove this, we're just evaluate and try to prove it pointwise. We want to show that for each M in O on colimit over disk over S1, the mapping space in OC from M to D, and now there's this map going to the mapping space in OC from M to S1. I want to show that this is an equivalence. And so now in this form, what is this map is doing here? So it's really composing, post-composing with a given bordism. So this is this bordism is a bordism from a bunch of disks to S1, and there's a canonical one, which is you have your incoming boundary, which is a bunch of disks. Your outgoing boundary is a circle, but you have to fill up your surface by adding some free boundaries. And so this is going from n copies of D1 to S1, and we call this object Cn. So the maps here are given by post-composing. So you have, maybe you have some manifold M here, and you have bordism from N to a bunch of D1s, and you glue on this canonical Cn, and you get a bordism from M to S1. Okay, and so this being equivalence means that
Were your disks numbered?
huh?
Were your disks somehow enumerated? I mean, it seems like the numbering of the disks is important to get
Yes.
that.
Yes. So each D is canonically just.
It comes with an order. Okay.
Yes. I mean, and in particular because these are disks with a map to S1. So this gives you, in fact, cyclic order. Okay, and what does this mean for this to be an equivalence? So, in other words, we want to show that for each W is a point in here, and we take the fiber, XW should be constructible. If we can prove this, then we can show that this is an equivalence. But what is the fiber, right? This maybe looks a little bit terrifying. You're taking fibers of a map of mapping spaces. Maybe let's just forget about the colimit for a moment. So, and let's take one particular n. So I map from mapping space of OC from M to n copies of D1, and then I post-compose with Cn to mapping OC from M to S1. So, and once I fix the point here, so the fiber here is really all the ways of factorizing W. So this fiber here, so morally speaking, I have a fixed map from M to S1 given by W, and also have a fixed map called Cn, bordism from the joint union of disks D1, n copies of them, and I'm looking at all ways of factorizing this bordism. So in other words, so now I'm fixing this whole thing called W. No, okay, so this is a lie. There has to be some circle boundaries here for this to be a composition. So okay, maybe we draw a better picture. So I have my fixed bordism M with outgoing boundary S1. And it has to have some free boundary somewhere. Let's say there's a free boundary here, and I want to find canonical way of decomposing W into Cn. So this is a copy of C3. And a bordism from M to D3. 3 copies of D1, and this will be our W. So this should be the fiber. So the point in the fiber should be a complement. It's really a complement of an embedding of Cn into W that fixes the boundary. So yeah, let me just tell you the answer. The fiber is really just an embeddings fixing S1 boundaries of Cn into W. But because we're really decomposing this bordism, so the free boundary had better go to the free boundary. So it should also send free boundaries to free boundaries. So free boundary should go to free boundary. So free boundary in Cn should go to free boundary in W. And for people who are more manifold-minded, so this really comes from the place sequence. I don't think I have time to define it, but yeah. So there's a rigorous argument to that, but it's our embedding space. So again, it looks a little bit complicated. So these bordisms, W can be some monstrous bordisms between one manifolds, and how are we ever going to study embedding space between them? So luckily, we can do the following maneuver. Blank. Okay, good. Yeah, so we want to study ways this embedding space of these CNs into a fixed bordism W. So this one, and okay, I'm actually repeating what I'm saying here. But so first we know that such embedding space are actually always has contractible components. This is a classical result of Grumman. And furthermore, there's it sort of CN sort of retracts onto this little graph, which is you have the circle boundary and you have a bunch of points attaching to it. So the point being that because in this embedding, you really don't care about where the incoming boundaries, this little disk go, but you do care about this red boundaries. You want the red boundaries to go to the red boundaries. So all we need to record in such an embedding is where the red boundaries go. And therefore, given an embedding of Cn to W is really given an embedding of these 3 arcs going from the fixed boundary on S1, and such that the endpoints land in the red boundary. So these are the free boundaries in W. And so in other words, so the fiber that we care about, okay, so not the fiber, yeah, the fiber we care about, it's really just this set of such embeddings of arcs up to isotopy. And but there's still a little bit inconvenience because so these endpoints can go anywhere on the circle. So you can go to the circle can move around a little bit. It's a little bit noisy, but we can fix that by trying to contract our free circle boundary to a single point. And there's a canonical way of extending any such embeddings of arc to one that lands in the circle of the free lands in the center of the circle boundary. So this is really the set of embeddings of arcs into this manifold, but we contract the circle boundary to a single point. And so the end of our arcs have to land in these, either the center of our circle boundaries or somewhere on the interval boundaries. And it's also up to isotopy. So this is, as an end result, so we're really studying the following. So W prime is obtained from W by contracting, again, the free circle boundaries to the center. And we mark the center as a point in the interior of our bordism. And we also just pick a point on each of the disk intervals. So this embedding space is really equivalent to the set of arcs on this marked manifold W prime up to isotopy. And this is a name. It's a classical object called arc complex in W prime with respect to these points. So again, these are systems of n arcs going from a fixed point on a circle boundary to a bunch of marked points that are prefixed in W prime. Okay. So great. So now this is what our fiber look like. So it ended up being not too terrifying because it's really it's equivalent to just a discrete set. And so now what is the colimit of this entire fiber? So here I'm only telling you, so if I don't look at the colimit, this is the fiber, but colimits in spaces are stable on their pullback. So the fiber here is really just colimit over in disk over S1 of embeddings of, okay, maybe that's not right, D. The short unions of n copies of D1s. So this is equivalent to embeddings of Cn into our fixed W, fixing the circle boundary and preserving the free boundary. But we also know that these are really just the same as arc on the colimit of, okay, maybe I should, never mind. Maybe let me write it somewhere else. If I still have time. So in other words, the fiber at our fixed W is the colimit of disk over S1 and D1 embeddings Cn into W, fixing S1, preserving free boundary, and this is the same as system of n arcs in W prime with respect to a set of points P, which is one for every circle boundary and one for every closed interval. And using the fact that this is the same as the paracyclic category, so I wrote down a bunch of equivalents here. This is the same as, in fact, the same as the opposite of the paracyclic category. So this colimit is really indexed by, not only by delta op, but by a further cofinal subcategory called delta inch op. And now this is really the semi-sequential set computing the geometricalization of my R complex. So that is the geometricalization of the simplicial complex given by. So, okay, and so now we want to show that this is contractible, and thankfully this is again a very classical result by Hatcher and Wall. So if P is not empty, then this is contractible. And if P is empty, this is empty. And fortunately, because conditions in OC tells you that there has to be some free boundary, so P cannot be empty, and this shows that this is indeed contractible. And this proves our colimit computation, and therefore the entire theorem. And this is, again, where it's really important that we're working in OC, but not Bord's 2 partial. So in Bord's 2 partial, you can really run into a situation where there's just no free boundary in your W prime, so the colimit, this cannot be an equivalence because your fiber is empty, right? Okay, yeah, and okay, that's the end of my talk.
Questions for the speaker?
Yes.
Do you have or expect a sort of similar theorem for the dual notion of Calabi-Yau? So like smooth Calabi-Yau where I always forget incoming outgoing boundary, but where the other boundary is not.
Oh, you mean OC op?
Yeah.
No, it's also not true for the precise reason here. But there's a bunch of things actually does not work, not just here. But if you reverse the direction of, if you take OC op, this column is not true. The second column computation is not true. Again, in fact, the first one is also not true. So it's just computationally not true.
But so I guess the theorem that you proved about the structure that you get, the sort of
so you're asking about
filter for the
Well, I mean, I'm not exactly sure about what. So our theorem is really about canonical extension given an open field theory. We're not claiming that we classified open closed field theory.
Okay.
It's actually pretty difficult, I think.
Yeah.
Thanks.
Do you expect to say something similar for twisted E1 Calabi-Yau objects?
Yes, so one thing you can do is cheating. So you can always modify the Picard group of C. But then to specify what the action is, you have to do a little bit of work. There's some twisting that's going on. I think that's probably the easiest way to fix this.
But do these also admit some sort of classification as symmetric nodal functors from some variant of O?
Yes.
Can you look at some computations maybe on like what kind of operations you get in conjecture?
That is a pretty good question. I mean, okay, probably not yet. It's pretty hard to. I mean, okay. So the one concrete example we have is free loop space. It's like cochains on M, and it's sort of the one case where we can actually explicitly write down what the factorization homology is cochains on free loop space of M. But you know, this is sort of what you expect.
You said you get actions by like the cohomology of BDiff of surfaces with mark points.
Mm-hmm.
Is that sort of compatible for getting points? Like, do the mark points really give extra structure, or does it all factor through the one without no mark?
Yeah, it should be compatible with forgetting points. And I mean, of course, it gives extra structure on your Hausdorff homology because you know without maybe with a little bit of caveat, but without the punctures, it definitely still the BDiff still acts on Hausdorff homology, but now we're also allowing it to have punctures, right?
But the action with punctures could factor through the one without?
That I am not sure. So I mean, okay, so these really come from morphisms in OC. So then you're just asking, are there morphism, like natural transformation between these morphisms, but there's none because, you know, each path component is really BDiff. Yeah.
Well, looks like our speaker is